Hello all, welcome to EPG Pathshala, and we are going to take a journey forward in learning about the technology GIS. I am Dr. Seema Mehra Parihar and I specialize in natural resource management and geospatial tools and technologies. I've done my PhD using them and even a postdoc from ITC Netherlands, and again I've learned and I've taken a journey on web GIS from there. And nowadays involved in a lot of convergent projects from DSJ, UGC, ICSSR project, and let us now join hands in learning about data models in geographic information system. The learning objectives of this lesson are: number one, spatial data observations focus on noting the locations. Every object, area and phenomena have unique latitude and longitude coordinates. In this chapter, you will learn about the following: the two primary types of spatial data in GIS, to recognize the nature of raster and vector data models, and we will also be able to understand the difference between raster and vector data in GIS. We will also be able to know when should we use raster and when should we use vector. There are only two key words in this chapter: raster, vector, and the third one is data model. By now, what has happened is that if you recollect your GIS learning from the previous lesson, what is GIS? GIS is Geographic Information System or Geographic Information Science. It is CSRTAT, captures data, stores data, retrieve data, transform data, analyze data and display data. Which data? Two types of data: spatial data and aspatial data. Why is it important? And why is it important? Because today there is so much of data and we all are talking about the big data. The real world around us is not uniform in some mode. It is undulating, irregular, dynamic, and to represent that geographically in a digital mode requires the understanding of data models, the major premise of this chapter. In developing a GIS application, real world features need to be translated into simplified representations that can be stored and manipulated in a computer by a computer. What is a data model? Data models provide a way of visualizing and researching about the world in an organized and structured way, in a digital domain. Data models are a way of organizing any object, area or phenomena that we wish to study in all levels. Data models therefore can be conceptualized as an abstract language, a collection of words, along with a grammar by which we describe the subject. To understand data models, let us recapitulate the spatial data. We know that there are two types of data: spatial data or spatial. Spatial data is that which has physical dimension and geographic location on Earth. The geographic location of all the object, area and phenomena present on the earth can be documented using different methods and technologies. Spatial data stored in a two-dimensional or three-dimensional maps and models can be further described by their respective entity, attached attribute and subsequent developed relationship. Three things. Whereas entity is a distinct spatial object like tree, river, house, etc. Attribute is a description about the entity like type of species, name, origin or the address of house, owner, number of family members, etc., which may be qualitative or quantitative in nature. And finally, the relationship describes the spatial location, that is association among it. For example, the tree which is there outside your home. Of course, you are having a tree, look outside the window. Its species type is an attribute information. Name, width, length, origin, attributes, all those which are there. Say it's a branch, it's a yard, it's on trees, eucalyptus and so on. Besides that, there is a two-way relationship. The relationship represents the link between the two different entities. A map depicts variety of information. For example, position, spatial relation, type of feature and measurable quantities. So, all this is something which is there. So, what we are going to impress upon you is a factual thing that you have a spatial data which has a lat long location, and you also have an attribute which is attached about that location. Say your house in which right now you are watching this particular lecture in case if I mark lat long values to it, that is a spatial data. Address of your house, who all stay in your house, how many rooms are there, is an attribute information of your house. So, all the geographic data that is there, it definitely must be represented in a simplified form, so as they can be stored in the computer. So, that means simplicity. Hence, they are represented by 3 geometric entities, and these 3 geometric entities are point, line and area or polygon, as we all see it and we all know it. So, now that means we remember point, line, area, spatial data. So, now let us come to data model. Data model is a description, portrayal, explanation and view of the real world. A data model is a conceptual idea as opposed to the way that the data is actually stored in the computer, which is the data structure. A data model is a mathematical formalism. It is a notation for describing data together with a set of operations used to manipulate that data, manipulate the spatial and spatial data. We can define data model as a set of guidelines for the representation of the logical organization of the data in database, consisting or having named logical units of data and the relationships between them, as Peck says. Define a data model as a general description of specific groups of entities and the relationships between these groups of entities. That is another way of understanding data model. Another way we can say is a data model is a formal system in which the set of precisely defined objects can be manipulated in accordance with a set of precisely predefined rules without any regard for the meaning or real world interpretation of these objects or rules. So, now what we need to understand is, say for example, you are in a house. Now, that house has rooms. That has to be actually, the scale can be diminished, but the position of those rooms cannot change. Your kitchen will be where kitchen is. Your room is where, and the room in which you are watching this program is that. So, reality of the information cannot go wrong. Complex it is, yes. We have infinite amount of information, yes. But the difficulty in defining a comprehensive and useful data model is to find a formal system whose behavior represents the informal behavior of the real world as closely as possible. Underline, as closely as possible. The real world can only be represented through models, M-O-D-E-L-S. Different models represent diverse conceptualization of the world with assorted outlooks and varied perspectives. The real world is represented into a data model using varied and sometimes a fairly high level of abstraction by means of using different operators for simplification and selection. And we need to remember this. We all therefore understand that a geographic model is an abstract and well defined system of concepts and respective vocabulary to describe and reason about real world, the world around me and you. The most familiar model of geographic information is a map you all are familiar with. It can be 2-dimensional, 3-dimensional, where conventions and rules are largely followed. Blue color represents river, red settlements, green topography, your trees, and we understand, recognize the human eye is the one that recognize shapes and forms, but the computer needs to be instructed on exactly how spatial patterns should be handled and displayed. Computer looking at a tree doesn't know that it's a tree. Computer doesn't know that this house which looks like square is a house. Computer doesn't know that a pond which I can see is a pond. Computer doesn't know that an irregular line that I am seeing is a river, or a straight line that I am seeing is a road or a tube well. You need to instruct the computer for it. So, in other words, what I am trying to tell you is computer requires descriptive information and instructions to turn the spatial entities into graphical form. The constructions of spatial models passes through numerous stages of data abstraction. In database terminology, the way of representing data is known as data models. We need to recognize that data models and data formats are two different things. JPEG images, DBF and all that are formats. Data models are something much more than that, and that's something which we all definitely need to recognize, that these two things are not same, neither similar. We have in a GIS framework two types of data models, and we all of course know that the world features exist either as objects or phenomena. Objects are discrete and definite, such as trees, buildings, huts, your car that is there outside your home. All these are objects. Phenomena are distributed over a large area, such as temperature, soil, floods. All these are phenomena, synomeny. So, all these are things are there. So, we need distinct approaches. There are object oriented based approach and there is a field based models. We need to of course work towards it. We need to recognize the object based spatial database which are there, that are the ones which are obtained by field surveying, remote sensing, image analysis, photo interpretation, digitization and so forth are generally represented in the form of coordinate lines as termed as vector data models. And we all geographers of course recognize that, you know, we have grids, we have latitudes, we have longitudes and we have georeferencing system. When the spatial database is structured on the field based model, the basic spatial units are different forms of tessellation. Regular as DEM. Do you know what is DEM? DEM is digital elevation model, or irregular as TIN are termed as raster data model. An identification of features from the real world followed by the selection of appropriate spatial data model is so important for raster or vector, and their structure are the key to the spatial model building process. All the major GIS and CAD software packages are either vector or raster based. Let's now remember what is GIS and what is the difference between GIS and CAD. GIS is Geographic Information System and CAD is Computer Aided Design. What is the difference? Of course, I know you know it. GIS you can answer, you can ask questions, you can do query building. CAD is you have drawn once, you cannot go ahead or simulate or design models on that. You have to redo it. So, GIS is in a way that science which enables me to ask questions from those models which I have created. So, largely some are software are vector based and some are raster based, and they extend functions to support other data structures. Let us now learn about the raster data model specifically. Raster data model is one of the variants of the field based model of geographic data representations, and these are made up of grid cells. You know what is a grid cell? Grid cell, a small spatial unit with square shaped lines and uniform adjacent pixels all arranged in order, where each pixel has its own value or class covering the whole database extent. It is an array of matrix arranged in rows and columns. Each pixel has a value and values indicating the characteristic of the phenomena it represents. So, in a way we all now can visualize a raster matrix. It is an array of matrix arranged in rows and columns, and inside that small box, what we call pixel, you have a value ascribed to it. There are two kinds of them, either discrete or continuous. That means there are discrete rasters and continuous raster. Discrete rasters have distinct values, distinct category and distinct theme. For example, one grid cell represents a particular land use or land cover class, and each thematic class can be distinguished and specific class allotted to them. They have a clear beginning and end and usually have allotted integers representing each class or interpretation keys. For example, in case if you look at it, we give them 1, 2, 3 because computer has to be told Remember, computer do not have that sensibility which you and me have it. Value 1 may represent vegetation, value 2 represents water body, and value 3 represents urban areas. You have to tell computer for it. It's not that the computer will automatically recognize them. Then we have continuous rasters. Continuous rasters and non-discrete rasters with data changing gradually as represented in a slow map, elevation grades, soil distribution, etc. They are generally represented with fixed registration points. Do you remember in your thematic atlas which you would have made ever? Slope maps, soil maps are not having boundaries. Your water maps are not having boundaries, right? So, but here we need fixed registration points. For example, your digital elevation models, that DEM what we call, digital surface model, DSM what we call, and DTM, digital terrain model, each have their unique registration points. Remember, every point that we are telling computer has to be unique, and every point that has to be recognized in any model, there has to be a unique registration points. So raster data, so that's in our memory. Raster data is also referred to as a lattice or a tessellation model. Tessellation, I know you know it, your English is very good. Tessellation is an infinitely pattern that generates, continuous. So raster data, tessellation. Tessellation is a space filling mesh, either with explicit boundaries as a mesh of polygon or with an implicit mesh as defined by a matrix of values in the logical model, and perform a discretization of the geometric area of interest. And a tessellation, we all recognize, may be either regular. Mesh elements are all the same size and the shape, or irregular. Sometimes elements of a regular mesh could be squares, rasters, we all recognize array of matrix, rectangles or hexagon cells, and they all are interconnected to create a planar surface representing all the space of a single area of study. The matrix of cells organized into rows and columns is called a grid. So now the new word, grid. But for geographers, grid is not a new word. GIS speaks your language. So in raster data model, the focus is more in location. The size is also known as MMU, minimum mapping unit. Minimum mapping unit on 1:50,000 scale is say 3 millimeter and 3 millimeter or 2.5 hectares. The value assigned to each cell is known as the gray value. It is also called sometimes like a brightness value, pixel value, reflectance value. All these are the names of the same thing, but generally in this remote sensing world we prefer either to call it a gray value or a brightness value. In an 8-bit system there are definitely 256 gray values and a raster image ranging between 0 and 255. How do we calculate it? I know you all know it, but just in 8-bit system, we do it. Yes, how do we do it? 2 raised to power 0 plus 2 raised to power 1 plus 2 raised to power 2 plus 2 raised to power 3, 2 raised to power 4 plus 2 raised to power 5, 2 raised to power 6 and plus 2 raised to power 7, because my first was 2 raised to power 0. So that makes it 256, 255 actually, and then 0 is 1. So 255 and 0, it together makes it 256 gray value, so the brightness value. A row and a column number represent each grid cell. A single cell is assigned only one value. Remember, single cell, whatever resolution, represents only one value. Objects that have several attributes are represented by a number of raster layers meant for each attribute. It generally happens that a single cell covers part of 2 or more objects or values. In such cases, normally what happens? The value assigned is that of the object taking the larger part of the cell, or of the object at the middle of the cell, or that of an coverage and an average for the whole of the cells. So what did I tell you? 1, 2, or of the surroundings, we create an average. You remember your statistics fundas of mean, mode, median, filters and all that? That's something which we all have it here. We all follow the same simple mathematical rules here, but we follow rules. The raster model provides simplest way of storing spatial data. The smaller the area of land that each cell represents, the higher the resolution of the data, and higher the spatial accuracy, and larger the file needed to store the data. And that's something which is so very important. Topology relations in raster data are not very strong. Just remember that. If the values of rows and columns are not known, then only the location of the neighboring cells may be calculated. And something which you remember, your interpolation, contour interpolation and all that, we do it here also. In other words, its relation to the origin of the matrix defined topology of the pixels. Example, top left corner of the image and so on and so forth. So that means, what have we learned? We have learned till now that the raster data is a data arranged in an array of matrix of rows and columns, largely square size, square shape, but there are other also which we have. We have rectangular and so on. Let's now come to the next data model. Which one is this? Yes, you're right, it's vector data model. So what is a vector data model? Vector data model or vector GIS is simply a generic name to describe a class of GIS that use a vector data structure to describe, represent and use spatial objects. A vector is a physical quantity that requires both magnitude and direction. Remember, MD, magnitude and direction for its description. This means a vector can be represented graphically by a directed line segment. An important property of vectors is that when they are oriented in the same or opposite directions, they can be added or subtracted, just like numbers with plus and minus signs. So you have to be very careful when you are digitizing. My advice, though even today a lot of software allow us to digitize in any direction, but my advice to each one of you, the one who is listening to this lecture, is simple, that please digitize in a clockwise manner. Why? Because when we are subtracting, when we are editing, at least we know that we have moved in digitizing in a very clockwise manner, so that makes it our job easier with the vector data. I want to play with it. Of course, we will be playing with it. I play with GIS. Vector data is not made up of grid of pixels. Instead of vector graphics are comprised of vertices and paths, VP, vertices and paths. The three basic symbol types for vector data are, remember your old GIS, PLA, point, lines and polygons. A point is specified by location XY in the Cartesian coordinate system. And we know, and we as geographers are so familiar with Cartesian coordinate system that we know, when the moment I talk about that, and for the ones who are listening, we call it what? We call it latitude and longitude. So that's something which is so very important. That's aligned by a sequence of connected points known as vertices and the polygon. And a closed area is a polyline having the same starting and ending point. So from where you start, you end there. The selection of geometric feature used to model a geographic entity to a large extent depends on scale and size of map. So scale is very important, size is very important. For example, Uttar Pradesh may be represented as a point on a small scale map like any world map, but on a map of India, Uttar Pradesh should be represented as a polygon which may have a number of points. And even, say for example, your NCR region, say or Delhi, it may be a point on a world map, but the moment we talk about map of India, it's a polygon. Polygons in a spatial framework are of two types. We have adjacent polygons and we have island polygons. Adjacent polygons can be visualized as adjacent countries represented on a world map where the common boundaries of two or more polygons, say for example India and Pakistan, yes, Bangladesh, India and Bangladesh have common boundaries. Plot boundaries, your next door neighbor boundaries are all interconnected. In a rural space, adjacent plots with common agricultural land have common boundaries. These are all adjacent polygons. Island polygons are the regions where occur in number of situations. For example, presence of pond in a big lake or presence of pastoral land within the forest. And you remember your oasis definition? Yeah, it's an island. In addition, we also need to remember the significance of attribute data. In the words of Haywood, remember this definition. I want all of you to remember. That is, spatial data are where the things are and attribute data are what the things are. What did I say? Let's say it 2 times. Spatial data are where the things are, and attribute data are what the things are. The 3rd time. Do I need to say that? Spatial data are where the things are, and attribute data are what the things are. It means attribute data attaches quality to the spatial data. Attributes are descriptive information about specified spatial objects. They often have no direct information about the spatial location, but can be linked to spatial objects they describe. Therefore, it is often to call attributes non-spatial or aspatial information. Since all the information cannot be represented by geometry alone, Therefore, it becomes necessary to attach the quality, example name, number, etc. It describes some aspects of spatial data, not specified by its geometry alone. But the problem is that it is a domain specific. That is, the spatial data for different analysis of the region remains unchanged, whereas the attributes keep on changing as per requirements. For example, it can happen that you have your nursery in a neighborhood, that nursery becomes a primary school, but the location of the nursery remains there. Any single land use, so that means that land use can, location of that particular creche is there, but that creche becomes say a play school later on. So that means location remains the same, but the attachment remains the same. Say you have a house today and you are living there, tomorrow you convert it into a shop, location remains the same, but the land use changes. So that is an attribute information. Vector data model is an object based approach to the representation of the real world features and is best used to represent discrete objects. That is, it represents anything from a simple number to a complex entity. It is a familiar coordinate geometry representation of specifying a point, line or polygon by two-dimensional Cartesian coordinates because of the assumption that the real world can be divided in clearly defined elements. Of course, because we all forget when we are doing that we have altitudinal driven spaces. By using one of the pair of coordinates, spatial objects are identified and represented by one of the three forms of basic graphical element. Such spatial objects have locations depicted simply as points, lines or areas, as told you before. Such spatial objects also have attributes. Since most of the thematic mapping for GIS are based on polygons, most of it, their storage and manipulation has received considerable attention. The characteristic of a polygon is that it must have a unique shape. You agree with me? You look at the map of India and you know it is India. Area and perimeter. The representation of a simple polygon with few points is straightforward, but when complex entities such as more than two polygons are stored, adjoining boundaries will be entered twice. Don't you agree? It will cause duplication of adjacent line and will create matching problem. Say now this is it and you have this. So this line is common with A and this line is common with B. So should I store it two times or there is a way for it? Yes, of course there is a way. Computer is very intelligent, but who makes it intelligent? You and me. Human being makes it intelligent. To overcome this and related problems, there are largely two models. First is the spaghetti data model, also referred as non-topological or geometric or both topological model. This is something which we will do in the next class. As the name suggests, it is a direct line-by-line translation of vector map. Each entity, that is point, line or polygon, becomes a logical record in the digital file and is defined as string of xy coordinates. And second is the topological model, where topological data define the logical connection between points, lines and areas with the surrounding parameters and the geographical description around us. This part would be covered in detail in the subsequent chapter, as I told you. Now is the time. Now we have learned raster, we have learned vector. Let's move to the difference between these two. We have understood now what is raster and what is vector. Therefore, of course, we should know and we should be able to compare these two and understand the advantages and disadvantages of two. But so now how should we do it? How should we go about it? We learn that the real world is that in which there is a format that requires to tell computer that this is it is. They could be raster or vector and both have their advantages. I am saying both are possible. So in case let us look at the raster data and the advantages and disadvantages. Raster data model answers the question what geographic phenomena occurs at this location. Advantages of the raster data are rooted through the basic nature of the data. Primary focus of the raster data model, as we know by know, is location. The geographic location of each cell is implied by its position in the cell matrix, well represented in a Cartesian coordinate system and stored as rows and columns of cell values, looking at the whatever the bit system it is. Due to the nature of the data storage technique, data analysis is usually easy to program and quick to perform. Raster based GIS allows the satellite data to be readily incorporated, no problem. But do we do it? That is a big question. The raster model can also represent gradual transition between a feature and surface, such as soil classification and elevation. It's very well suited to many spatial modeling operations, mathematical modeling operations, and also a lot of quantitative analysis, such as optimum corridor route selection or modeling surface, storm runoff, forest fire spread, and all those wherever we have a continuous data like elevation data and so on. Further, grid cell systems are very compatible with raster based output devices. Example, electrostatic plotters, geographic terminals, all can be very well done, but again there are disadvantages with this data. Lot of disadvantages. Number one, the non-continuous entities such as roads and boundaries are not very accurate. Houses, points, the raster data have reduced spatial accuracy. It means raster model represents a more generalized view. But sometimes for reconnaissance work that's good enough. Line and point data in raster will always be less precise than in the vector format. But do I actually want accuracy? This is good enough. As raster consists of evenly spaced data that covers a certain area, data that is spaced evenly in one attribute may in fact be unevenly spaced in another due to a lot of distortions. It is especially difficult to adequately represent linear features depending on the cell resolution. Accordingly, network linkages are difficult to establish in raster data. Further, the cell size determines the resolution at which the data is represented. Raster data sets become potentially very large because they record values for each cell in an image, wastage, redundant data. With the increase of resolution, the size of the cell decreases. Consequently, cost for speed of processing and data storage also suffers. Moreover, what happens is processing of associated attribute data may also become cumbersome if large amounts of data exist. And we know today is a world of big data. Calculations of areas and distances though easy, but calculation of parameter is more difficult because it distorts, no? If you arrange data in a grid. Yeah, now you are with me. Raster maps inherently reflect only one attribute or characteristic for an area. Since most input data is in vector form, data must undergo vector to raster conversion. So another wastage of time. Besides increased processing requirement, this may introduce data integrity concerns due to generalization and choice of inappropriate cell size. It's up to me. So again a problem. Most output maps from grid cell systems do not conform to high quality cartographic needs. Cartography, we all understand, is two A's, aesthetics and accuracy. Here we are not being so accurate. A truly variable surface cannot be easily compressed, and that's another problem. Raster is faster, but vector is correcter. Another word which you remember, you need to remember. Now let's look at the vector data and the advantages and disadvantages. Vector data model, as we have observed above, has many advantages. Primary focus of the vector data model is a geographic feature, therefore is more suited to the question of what do I know about this geographic feature. All elements are located as xy coordinates in a Cartesian coordinate system. That means accuracy is very high here. Aesthetically also more pleasing. Accurate feature shapes, well-defined boundaries. Observation units and the endpoints can be clearly marked. Emphasis is on relationship and distribution of geographic features. Calculation of area and distance and perimeter is easy and precise. Process of data conversion too is reduced because most available maps are in hard copy and are in vector format. Further, vectors use minimum space for storage of spatial data. Topology rules can help integrity with the data model, and therefore with efficient encoding of topology, more efficient operations that require topological informations, including network analysis and proximity analysis, can be processed here. So the disadvantages of the vector data are largely related to the inherent nature of data, where location of each vertex needs to be stored explicitly. For example, geoanalytics of all kinds is important for each vector data to be converted into a topological structure. With static topology, any kind of updating with extensive data, vector data, cleaning is required, and rebuilding of the topology most of the time becomes important. Further, the algorithms required for any analysis with vector data are complex, very complex, processing intensive and time consuming. Further, continuous data of any kind is not effectively represented in a vector form, and they require substantial generalization and complex vector manipulations. Spatial analysis and filtering within polygons with vector data seems difficult, and to an extent, frankly, not possible. I know, my friends, by now you're confused. Raster is good or vector is good, looking at the advantages. But most standard GIS operations can be performed in both data models. Which data model is appropriate? Of course, if I only have one software which is in lakhs, I'll use that database which is conducive to my software. The quick question pondered over while making a selection are following. Four following questions I tell you. Number one, what is the required map scale? If the scale and the time is not an issue and you can work with any scale of data, the preferred choice would be vector data, right? Vectors can scale up the object to any scale, but this flexibility is not possible with the raster data, right? So, depends on scale. Number two, do you want to work with pixels or coordinates? Make a choice. Vector data whereas work with coordinates, the raster data work with pixels. So, it depends on what you want to use. Third, do you have any file size restriction? Raster data file size can result larger in comparison with the vector data set with the same phenomena. Make a choice, make an intelligent choice and impress people around you. Oh my God, I know my raster vector bed. I can make a choice. Number four, frankly speaking, are you restricted by a particular GIS software? Many of us poor academic scholars living in developing countries are restricted with that. So, whichever data, say in case of vector data models, if I am having and working on ArcInfo coverages, GIS shape files, CAD, GBF, Tiger, etc., TIGAR, etc., I have to use vector data. However, raster data models will be preferred and used when using ArcInfo grids, images, digital elevation, DEM, PNG, JPEG, etc. So, but it is very important in case if there is no limit, I can make a correct pick. So, what have we learned today? That real world around us is not uniform and smooth. I want to be accurate with my research. I have to design, I have to pick up, I have to select a geographic model which either is raster and which vector. If today I have created a database and I am not using it tomorrow because I moved to a different space, whoever is using that database is conversant with that data model. So, for me, it is important for us to recognize and make a correct use of raster and vector data models in case if we want to do a true research and we want to make a correct knowledge base so that people in continuation can make use of it. Locations in a vector data model are referred by XY coordinates which can be linked to form lines and polygons and attributes and referred through the unique ID numbers. Images from remote sensing, scan maps, elevation data from USGS, etc. are all in raster format. Census data is all in tabular format. So, the format of my database is important and I have learned through this chapter how to do that and also to recognize that which data model is best for my type of work. I hope you all would have enjoyed this lecture and you all would have definitely become much more informed about your database structures. My only request to each one of you is learn your database correctly, spend some time looking at it and design it accordingly as per your objective, as per your purpose, as per your aim of research. Enjoy creating data models and enjoy GIS. Thank you.